Hello everybody, this video is going to cover some of the calculations that we can do for the solutions chapter. The solutions chapter is mainly concerned with the concentration of our solutions. The thing is, there's lots and lots of different ways you can express concentration, lots of different units that you could use. In chemistry, we have a tendency to use certain ones. In biology, they have a tendency to use different ones. In environmental sciences, they like other units. So it kind of depends on which branch of chemistry or science you're doing. Some tend to be more common than others. What we like to do in this chapter is expose you to a variety, because that way, whatever class you tend to take after chemistry, you'll have at least been exposed a little bit to the various ways that we can calculate our concentrations. So let's go over some of these. There are going to be some assumptions you need to make, okay? So the first assumption, unless you're told otherwise, is you assume that your solvent is water. Water is what we call the universal solvent. In chemistry, we almost exclusively use water. Sometimes we may use another solvent, but you would be explicitly told because that would be less common. The other thing you're going to assume, unless told otherwise, is that the density of your solution is the same as water. It gets a little bit trickier if you have to start recalculating densities. And so to make things a little bit simpler, we just assume that the solution will have the same density. If you're told otherwise, then you use that information for the question, but it's not very common. So the first one we're going to look at is called mass percent, or percent composition. So it's a ratio of masses, and we express that as a percent. You're going to see that it's going to be the mass of the solute divided by the mass of the solution. And then make sure you times your answer by 100. Sometimes people forget to do that. One of the things that's really important is that you pay close attention to these little vocab terms here. This is not solvent on the bottom. This is the mass of the entire solution altogether. You have to remember that the solution is what you get when you have the solute plus the solvent. So if you have 5 grams of solute and 100 grams of solvent, your mass of solution would be 5 plus 100, right? It would be the sum of the solute and solvent. So you have to make sure you're paying attention to those vocab terms so that you know which numbers to put down here. Okay. The next is something we don't use very often in chemistry, but it does get used more often in something like an environmental science class, which is parts per million. This is a great one when you're dealing with very, very low concentrations, which is common in things like pollution, right? And so it gets used a lot in a class like that. So it's exactly the same. The only difference is instead of multiplying it by 100, we multiply it by 1,000,000. That way we get numbers that are a little bit more easy to manage. Otherwise you'd have a very, 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 very small number, which can be annoying. The biggest problem I have with this part is people forget what 1,000,000 is. They'll punch a bunch of zeros in their calculator for that number and then they miscount. So be very careful. When you multiply it by 1,000,000, make sure you're actually multiplying it by 1,000,000. All right, another one that does not get used as much in chemistry, but it does get used a little bit more in biology, is grams per liter. So grams per liter is exactly what it sounds like. It's going to be the mass of the solute divided by the volume of solution, and it would be, that way typically you're making up 1 liter jugs of this stuff. We like to call this the quick and dirty unit because it does not take very much thought. And so, you just weigh out some grams and you throw it into a liter container and you fill it up with water. The problem is as you've learned all year, grams is not a very good unit in a chemistry class because the mole is really what we deal with when we're doing our stoichiometry. Remember, comparing apples and apples. And so we don't like using grams per liter in chemistry because it's just not a good match for the types of problems that we're using. In biology, they tend to use this more because the solutions they're using, they don't really care about the solution itself. They're just using the solution for something biology related. So as long as they know how to mix up the solution to use, it's good enough for their purposes. So that's why you may see this in biology a little bit more. All right, next is mole fraction, which you've actually learned in the gas law chapter. Remember, mole fraction is the ratio of moles. We use a fancy looking X for our mole fraction. You would use little subscripts to tell people which substance the fraction is about. And it would be the moles of solute over the moles of total solution. So this is one more place where you have to make sure that you don't just put the solvent down here. You need to put the whole solution value. So even though this gets used for gases a lot, it could be used for this chapter too for any kind of solution that we're interested in. The last one is what we call the best one. This is the one we use in chemistry all of the time. It's called molarity. This is very similar to grams per liter, but instead it's going to use moles, which for our purposes, remember, is a much better unit to be using. So molarity is moles of solute over the liters of solution. You should be noticing that most of these have that solution value on the bottom, and solute is on the top. This is the one that we use all the time. So if you went into the chemical stock room on campus and you looked in our cupboards, all of the bottles would be labeled with molarity. When you look at your lab sheets from the year, you'll notice that the concentrations of the chemicals are listed with the molarity so that we know the concentration. It's very convenient because it'll allow us to go straight into our stoichiometry problems because we can get to moles very quickly. So let's do a couple practice problems with molarity. If you have 734 grams of lithium sulfate and you dissolve them in 2,500 milliliters of solution, what's the molarity? So the very first thing we need to do is convert into moles. Using our molar mass. We will put grams on the bottom so that they cancel. 1 mole goes on the top. And we end up with 6.68 moles of our lithium sulfate. Now I'm going to do my molarity calculation. Moles of solute, which we just calculated, over the liters of solution. That's the big deal. Do you notice I had to convert? I do not leave it in milliliters. We do it in liters. And I find out that my solution has a concentration of 2.67 molar. You could leave it moles per liter, MOL over L, that's fine, but we often use a capital M. Make sure that you do use a capital M. A lowercase m is something different. It's called molality with an L instead of an R. And we're not going to cover that in this class, but in AP Chem that gets used a bunch. So do make sure that you're careful with your capitalization. All right, let's try another one. I'd like you to pause the video and try this one. Now, if you notice, they don't tell you what the concentration units should be. They're not telling you if it's parts per million or grams per liter. If they don't tell you, if they just ask what's the concentration, because you are in a chemistry class, you are going to assume that they mean molarity. Always assume it's molarity unless told otherwise. All right, let's see how that went. I'm going to convert from grams to moles. Grams will go on the bottom. 1 mole goes on the top. That way my grams cancel, and I'm left with moles. Now I'm going to do moles of solute over liters of solution, so I need to convert this. 3.5 milliliters needs to get converted into liters. Remember, you can use your King Henry to help you do that. Move your little decimal around. So you can see I put my moles on top, I have my liters of solution, and I get my final molarity. One thing to be careful of is that you do not always assume that your volume is the solution. Sometimes they may give you a problem where they tell you a volume of solute and then a volume of solvent, and you have to combine it to get your total final solution volume. So just be careful that you are reading slowly and paying attention to the words. You know, solute, solvent, solution, when you're reading quickly can kind of blur, and you kind of might make mistakes if you make an assumption versus actually reading the question. So just be a little bit careful. All right, the next thing is going to be about making dilutions. So if you think about it, it would not be practical to try to store in the chemical stockroom a bottle of every single compound in every single possible concentration. There's zero chance we could have a stockroom that could carry infinite number of bottles, right? So what we do in the stockroom is we have our very concentrated solutions in bottles. And when I need something, I'm going to take the concentrated solution out of the stockroom and I'm going to water it down and make it less concentrated. I'm going to dilute it into the concentration that I need. So, you know, I might need 1.5 molar, but in the stockroom I only have 6 molar. Well, there's a calculation I can do to figure out how am I going to water it down? How much water do I need to add to get the diluted solution that I need? So we call that equation M1V1 equals M2V2. The molarity of the strong stuff times the volume that you need to use is going to equal the molarity of the weaker, more diluted stuff times the volume that you need when you're finished. So I'm going to be able to figure out how much of the strong stuff do I need in order to water it down to the one that I'm actually interested in. So let's look at a practice problem. How much of a 2.3 molar solution do you have to use in order to make 750 milliliters of a 0.6 molar solution? So what I'm going to do is I'm going to figure out what are my starting values and my ending values. I'm starting with the concentrated stuff, but I don't know how much of it I need. So I'm solving for V1. I do know the concentration I need to end with, and I know how much of it I need when I'm finished. So when I plug that into my equation, I get M1 V1 equals M2 V2. Strong concentration on one side, the weaker values on the other side. Now some of you might say, wait, you forgot to convert your milliliters into liters. But I don't actually need to, right? If you look, when I solve for V1, my molarities will cancel. So my answer will come out in milliliters, which I'm fine with. If the question wants it in liters, answer in liters. But it's very common to do these problems in milliliters because we use graduated cylinders and pipettes and things like that to measure the volumes, and those are typically marked in milliliters. So it's pretty convenient to just leave it. So if you isolate your variable, you're going to find out that you need 195.65 milliliters of the strong stuff in order to make the weaker solution that you're interested in. So let's think about how we would physically do this. I'm going to have like little cartoon pictures, okay? Let's think about how much water did we have to add. Well, I have my beaker of strong stuff, right? This is the jug that I got out of the stock room. It's too strong. I need to water it down. So I'm going to take my empty container. I'm going to take out 195.65 milliliters of the strong stuff. I'm going to put that in a new container. Then what I'm going to do is I'm going to fill this up until I get up to 750 milliliters of my solution. I'm not adding 750 milliliters of water. That would be the solvent. I don't have 750 milliliters of solvent. I have 750 milliliters of solution when I'm finished. So I'm going to add up until I have 750 milliliters all together of my water. And you can see that we'll water it down, it will dilute it, it will reduce the concentration. So how do I find out how much water to add? Well, if I know that I need 750 mils total, and I know how much of the strong stuff is in there, it's just a subtraction question, isn't it? 750 minus the strong stuff will tell me how much water I added. Now in real life, because we're typically making up 1 liter at a time, we have fancy pieces of glassware that are measured exactly at a liter. And so it can be very easy to make our solutions. You put in your strong stuff, you fill up to the line, and you're all done. So we're not often making random volumes like this in real life. In your practice problems, yes, you might make strange volumes, but in real life we typically make a liter because we have liter jugs that fit nicely on the shelf. So sometimes we use that fancy equipment called a volumetric flask to make 1 liter at a time. So here's a picture of some volumetric flasks. You can see there's a 500 milliliter one, there's a 200, there's a little tiny baby 50 milliliter one. They do come in a variety of sizes. On our campus, we don't have a ton of different sizes because they are a little bit more expensive because they're so accurate. So we have some small ones, but I usually just make up a whole liter at a time. And that way I can also share with the other teachers, right? If we do the same labs, there's extra. So you can see, I don't know if you can see very well on the video, but if you look real carefully, there's a little white line on each of these flasks. That's the mark you fill up to. So you put your strong stuff down in the bottom, and then you fill up with your water until you get to that line. And then you can kind of put the cap on and mix them around, make sure everything's really mixed and swirl it and stuff. And then you pour it out of the fancy container and you just store it in a plastic, screw top jug in the stock room. So I like to show you how we make those solutions. If you ever become my TA, I have you make a lot of solutions, right? You can do a lot of that work and store that stuff in the stock room for me, which is very helpful. All right, everybody, that's it for this lesson. I hope that was helpful. Bye.